In this section, we're going to take a look at the law of sines.
Up to now, the triangles we've been looking at have all been right triangles. That is to say, a triangle with a right angle, a 90-degree angle. But not every triangle has to be a right triangle. But of course, all of the mechanics that we've had so far have required us to look at things that involve a right triangle. If you're looking at an angle in a triangle, and you're going to say, here's an angle theta, and the side opposite over the side adjacent, that's the tangent, and the side opposite divided by the hypotenuse, that's the sine of the angle. All of these require a right triangle. Not every triangle is going to be a right triangle. In fact, most of them are not. And it would help if I knew how to spell, right? Triangle. Most triangles don't have a 90-degree angle. Those are called oblique triangles. Whenever you have an oblique triangle, you might have something that has all angles less than 90 degrees. Or you might have something where one of your angles is more than 90 degrees. Now, of course, you can't have more than one angle that has more than 90 degrees, because if that's already over 90 degrees, remember that the sum of the three angles must add up to 180. So if you have two of them that are over 90, well, that's already more than 180, so that can't happen. So either all three angles are less than 90 degrees, or exactly one is more than 90 degrees. Now, all of the mechanics that we've had so far rely on a right triangle, which means if we're going to deal with oblique triangles, things that are not right triangles, we need to develop some new machinery. We have some new techniques to work with these kinds of triangles and these kinds of situations. Now, before we look at those, let's look at what the information that we have available to us is, and more importantly, what information we need. What I mean by that is, okay, if I draw a triangle and I tell you, okay, here are the measurements of the three sides and the measurements of the three angles, well, that's everything you could possibly know about a triangle. But even if I just give you some of the information, it may be enough for you to fill in the rest. Well, how much information is enough? How much information do I need as a minimum to uniquely determine a triangle? Well, it's going to turn out that we need half of the information. For any triangle, we have three angles and three sides. 6 pieces of information. If you have three of these pieces of information, then you can uniquely determine the triangle, meaning you can figure out the rest. Okay, so is it okay if I have any 3 pieces of information? Well, no. They have to be the right bits of information in the right combination. This brings us to what's called the congruence axioms. Now, before we formally state them, let's take a look at a little visual example. Let's say I told you you need to build a triangle. You need to draw one. You need to create a triangle. And you say, okay, sure. But I tell you, no, but you have some restrictions. You have to make the triangle out of these 3 side lengths. You can't cut them. You can't add anything to them. They may stay exactly that size. But using those 3 sides, you must build a triangle. Well, you don't really have a choice. If you have to use all 3 sides, you say, well, there you go. Well, no, that's not a triangle. It doesn't close. A triangle has to have all 3 corner points touching. If that's my only choice for side lengths, that's it. That's the only triangle I could build. Okay, maybe I could rotate it a little bit. But triangle, that's the only triangle I can build. Aside from maybe rotating it a little bit, that's the only triangle I could build out of those set of side lengths. So if I know the 3 side lengths, that means that I can uniquely determine a triangle. So if I know the 3 side lengths, and here we're going to write that as side, side, side. I'm going to write 3 S's for sides. If I know the 3 side lengths of a triangle, that means I can uniquely determine what triangle I have. Right? Because even if it's disassembled, and you tell someone you have to assemble it, well, they don't have a choice. If they're using those three sides, we must all build the exact same triangle. Okay. Well, what else? Well, what if I didn't give you three sides? What if I just gave you two sides? Well, you said we need three pieces of information. So what's the other piece of information? Oh, let's say we had two sides and the angle in between them. So consider you have this. This is made of metal, and I suppose you could bend this, but I'm nowhere near strong enough to do that. All right. So here, let's say I gave you these two side lengths. Here, this is about 4 inches, and here this is about 1 inch. And I told you, okay, now, by the way, here's an angle. And like I said, I can't really bend that angle. I'm not strong enough to do that. And I told you, okay, now you have to build a triangle out of these two sides and that angle. Well, even though and I told you, you can now draw any triangle you like. Well, there's not really a choice. If I'm going to connect these two, I can't make this any longer or any shorter. I can't make this any longer or any shorter. This side length and this side length must stay exactly as they are. And that angle in between must stay exactly as they are. Well, if I want to close the triangle, there's only one choice. I have to use that. Now, I could rotate it. Yeah, but that's still the same triangle. All the measurements are the same. The measurements of the three sides, the measurements of the three angles, everything about it stays exactly the same. So as long as I give you two side lengths and the angle that's in between them, well, then I have no choice but to build the same triangle every time. So if I have two side lengths and the angle in between them, well, then that requires me to have a unique triangle. There's only one option. Okay, what's the third thing I could do? Well, notice here I had two side lengths and the angle in between them. What if I did that the other way around? What if I gave you this object? And I told you, okay, here's a side length. And you have to leave that exactly the same. You can't cut this. You can't stretch it. It has to stay exactly like this. And now here's a couple of angles. And I know that's 50 degrees, and I know that's 40 degrees. All right, now, you can't bend this either. You can't make these angles any bigger or any smaller. Now, go ahead and finish the triangle. Well, again, you don't really have a choice. If you're going to connect these to finish the triangle, there's only one triangle that you could possibly build. Because, of course, a triangle has to be closed. It has to come all the way to the top and touch here. I can't make this any longer, because if it's any longer, it won't touch that corner. And likewise, if it's any shorter, it also won't touch the corner. So if I give you a side length and the two angles on the opposite sides of that side length, well, then I don't have a choice but to build that exact triangle. So if I have two angles and the side length in between, well, then I have a unique triangle. Now, at this point, it looks like you can get away with any three pieces of information, right? Well, no, not quite. For example, let's consider we have something like this. Let's say I'm going to take this side length, and let's say I'm going to take this side length, and let's say I have to have both of those, right? I'm not allowed to stretch this one or this one. I'm also going to have to fix this angle right here. I'm going to keep this angle the same no matter what. I won't make it any bigger or smaller. And now I'm told I have to make a triangle. Well, notice no one said anything about that angle up there. No one said anything about this angle. I could change this. So I could move this to make it larger, or I can move it to make it smaller. I can't change the length of any of these sides, but I can change the angle in between them. If that's the case, well, then there's more than one way to form a triangle. This angle must remain the way it is. Right here, this angle. This can't get any longer, and this can't get any longer. Well, I could just join them together like that. And there we go. That's a triangle. That angle stayed the way it was. Right there, that angle. This side length stayed the same, and this side length stayed the same. But you know what? If I just swing this out, I can make this longer, and I have another triangle. Again, that stayed the same. I didn't make it any longer. That stayed the same. I didn't make it any longer. And that angle stayed the same. This side length got longer, but that's okay. We didn't worry about that. So if I have two side lengths and an angle that's not in between them, notice over here the angle is in between the two sides. Here it's not. The angle is away from the two sides, then that situation would not lead you to a unique triangle. I could build that triangle and have the one angle and the two sides, or I could have this triangle, which is definitely a lot smaller, and still have that one angle and those two sides. So notice it's not just any three pieces of information that give you a unique triangle. So that's what our congruence axiom says. And here, let me write it out with a little more detail, so a few more words in here. The congruence axioms say that, here, let's write this on its own. You can uniquely determine a triangle, meaning you can learn everything about it and there's only one answer to it. You can uniquely determine a triangle if you have either 3 sides of the triangle, you have 2 sides and the angle in between them, and that's important. It must be in between, as we saw. If it's not in between, that's not going to work. 2 sides and the angle in between. Or 2 angles and the side in between. All right. And these are the only 3. If you have these, either 3 sides, 2 sides and the angle in between them, or 2 angles and the side in between them, then you can uniquely determine a triangle. Otherwise, you might be able to determine a triangle, but it wouldn't be unique. There'd be different answers to the same problem. Okay, so let's say I have one of these situations. Let's say I have a situation where I know I have a unique triangle. Well, just because I know I have one doesn't mean I know what it is. So how do I find it? Well, that brings us to what we call the law of sines. The law of sines looks something like this. So imagine you have a triangle, or you don't have to imagine, let's go ahead and draw it. And as usual, we can label the angles of a triangle. I'll call this A, I'll call this B, and I'll call this C. And as usual, we call the side opposite of the angle A, we call it little a. Opposite of B, we call it little b. And opposite of C, we call it little c. Okay? But for this problem, we're not going to really worry about C and little c. We're going to deal with just A and B, just for the purposes of this example here. So now imagine that you split this right down the middle. Right? Now, this doesn't have to be symmetric on both sides. It could be that this is 40 degrees and this is 42 degrees. Right? They don't have to be exactly the same, but here I'm just going to split from this point straight down. Well, that's called the height of a triangle. The height is the distance from the highest point straight down to the base. Okay, so now what? Well, I have 2 triangles, one on the left side, one on the right side. I've split my triangle into 2 smaller ones. All right, so now for this smaller triangle that's on the left, look at the angle A. The sine of A, well, look, this is a 90-degree triangle. So even though the original one was some triangle, maybe it was right, maybe it wasn't, doesn't matter, this triangle is right. Okay, so using what we know about a right triangle, we know that the sine of A is the opposite over the hypotenuse. So the sine of A will be h over b. Sine of A equals h over b. The triangle on the left, we can do the same thing. This is also a right triangle. If this is a straight line, if that's 90 degrees, that must also be 90 degrees. 90 plus 90 is 180. So now the sine of B has to be equal to the side opposite of B divided by the hypotenuse of that triangle on the right. So h over A. Now you notice here that h is the same, right? It's the same length here. It's the same variable there. So here, let me solve for h. If I multiply b to the other side, I get b times the sine of A. Well, that's going to give me h. I multiply that b over here. If I multiply a this way, I'm going to get a sine of b is equal to h. And now these two are equal to each other. H is the same as that h, which means this must equal to that. So I get that the side length b times the sine of the angle A is equal to the side length A times the sine of the angle B. Well, now, I can divide both sides by AB. I'm dividing both sides by both of those numbers there. The reason for that is now A divides A and B divides B, and I end up with a nice, simple, and reasonably easy to remember expression. And also it will explain why it's called the law of sines. For any triangle, regardless of what the triangle is, this didn't start off as a right triangle, it was just a triangle. If you take the corners and call them A, B, and C, and if you take the side lengths and label them A across from A, B across from B, and C across from C, then it must be true that the sine of A over little a is equal to the sine of B over little b. Just like that. It turns out that because we have these named arbitrarily, meaning we didn't have to say A, B, and C. We could have said A is up there, B is here, and C is here. It turns out that this is true for all of these angles, not just those two. So the way the law of sines is typically stated is, and here let's write this separately, law of sines. For any triangle, and we could give a description, but here I'm going to go ahead and draw it. For any triangle, A, B, C, and whose side lengths are labeled A, B, and C like this, for any triangle that looks like this, regardless of what the angles are, that doesn't have to be right or anything of that nature, as long as you have a triangle labeled like this, then it must be true that the sine of A divided by A is equal to the sine of capital B, the sine of the angle, divided by little b, and that's going to be the sine of capital C, the angle C, over little c. So this will help us to determine a lot about a triangle given pieces of information about it. So let's consider an example. Here we're going to solve the triangle, meaning find all of the missing pieces of information. Solve the triangle. And we're given this as a visual. We're told, okay, here's a triangle. Notice this is not a right triangle. This is just a triangle. And we're not given every bit of information about it, but we are told that this length here is 43. I almost want to call that the hypotenuse, but that doesn't really work here. Because remember, hypotenuse is the side opposite of the 90-degree triangle, the 90-degree angle. Here we don't have any 90-degree angles. At least it doesn't look like it. So here I'm going to hold off from wanting to call that a hypotenuse. It's just one of the sides of a triangle. Here, this is going to be 52 degrees. So let me write that in red here. This is 52 degrees. And here, this one is 29 degrees. And even though we only have 3 pieces of information, that is sufficient to give us the entire triangle. Why is that sufficient? Well, because notice the information we have. We have 2 angles and the side that's in between them. We have 2 angles and the side between them. 2 angles and the side between. When you have that combination of information, that's sufficient to give you a unique triangle, meaning there's only one answer, which we can now find. All right, so here, I'm going to go ahead and call this the angle A. I'm going to call this the angle B, just for the sake of labeling. So here, let's write down what we have. We have the angle A, and that's equal to 52 degrees. And the angle B is 29 degrees. The angle C, we don't know yet. It's right here, but we don't know the numerical value yet. Here, this is the side length opposite of the angle C. So here, that's little c, and that's 43. And I believe this is centimeters. Yeah, this is centimeters. Here, I should write that centimeters. All right. So now, this information is sufficient to give us our triangle. All right. A triangle has the side lengths add up to 180 degrees. So right off, we can figure that out. A plus B plus C must equal to 180 degrees. Okay, well, that means that C that we're looking for has to equal to 180 minus the A minus the B. We subtract both of those, that'll leave you the C by itself. But we know A and B. So here C is equal to 180 degrees minus 52 degrees, which is 128, minus 29, which will give us 99 degrees. Just like that. So let's go ahead and fill that in. Here that's 99 degrees. Notice this is not a right triangle as it appeared. It appeared this was not a right triangle, and here we can confirm that. That's definitely not right. There are no 90-degree angles. But now, hey look, I have an angle and the side length opposite of it. This is what cues me to use the law of sines. Because, remember, the law of sines says that for any triangle, doesn't have to be right, for any triangle, the sine of the angle A over little a is equal to the sine of the angle B over little b, which is equal to sine of the angle C over little c. But here I know both of those. So let me plug those in. Here I get that the sine of 99 degrees divided by the side length 43, well, that's equal to the sine of A. Oh, but I know A is 52 degrees. Sine of 52 degrees over little a. Well, I don't know what little a is, and I don't know little b either. Oh, but look, that's an equation, and a is the only unknown. That means I can solve for a. So here, I can go ahead and solve for a. Here, what I can do, let me go ahead and multiply out by a here on both sides. I don't want that in my denominator, so I can multiply times a. Just like this. And I don't want this in my denominator either, so let me multiply by 42 also. By 43. Just like that. So now a divides a. Now we're pretty sure a is not 0. It's not the side length 0, so that's okay. We know how to divide by a number that's not 0. And same thing here. 43 divides 43. And this will give us a sine of 99 degrees is equal to 43, these have divided away, is equal to 43 times the sine of 52 degrees. Oh, but now the a is almost by itself. I can just divide by the sine of 99 degrees, and I get my answer. So let's go ahead and do that. Just like that. And so this will give us that a is equal to 43 times the sine of 52 degrees over the sine of 99 degrees, which is an exact solution. That is exactly the right number. However, in many application problems, you often care about an estimate. You often care about a decimal number, less than exact value. So for that, we can always substitute in these numbers. We can plug these numbers into a calculator. So here we go. Make sure this is in degrees. So I'm switching my calculator to degrees now. So that's going to be 43 times the sine of 52. And then I'm dividing that by the sine of 99. And that gives me 55.2479773. Oh yeah, but remember, here all of our values are to the nearest whole number. And here you have a level of precision that's not justified given our information. So here this is, yeah, I know it's 55.247 something or another, but that level of precision is not really justified. So we're going to round it to the level of precision that we have in all of our other information, which here is to the nearest unit. Here, this is to the nearest centimeter. So here, we're going to go ahead and round this off. And yeah, I know that's not the exact answer, but that's what's called for. So here we're going to say that's approximately 55 centimeters. So here that's going to be approximately 55 centimeters. Now you notice that that is not exactly correct. It's only approximately correct. What that means is that we don't want to use this to find B, because if this is slightly wrong, then this will also be slightly wrong. And if you have two things that are both slightly wrong, it makes them both a little bit more wrong. Here, this is a value that was measured as closely as possible. So whenever you arrive at an answer, you're going to round it to get the right level of precision. Once you round it, that's not correct. It's very close to correct. It's what you need for the purposes of the problem, but don't use this 55 to find B. Here, let's go back to the one that we do know for sure. Here, we're okay using this one because this one was not rounded. Here, this was 180 minus 52 minus 29. That's exactly 99 degrees. So that's not rounded. Here, we're just going to repeat the same procedure, but with the other angle. Here, I'm going to say, well, look, sine of 99 degrees over 43 centimeters. These two pair together, C with C, C with C. That's equal to, well, I'm looking for the length little b, so I'm going to take sine of b over little b. I know b, so it's going to be sine of 29 degrees over little b. And now we're going to go ahead and repeat the same procedure here to isolate our b. Here I'm going to multiply on both sides by 43b. Multiply on both sides by 43b. Here the b's divide, here the 43's divide, and we're left with b times the sine of 99 degrees is equal to 43 times the sine of 29 degrees. Just like that. And finally, we can divide on both sides by the sine of 99 degrees. Sine of 99 degrees. These divide out. Sine of 99 divided by sine of 99, that's 0. Oh, sorry, that's 0. That's 1. And 1 times b will give me b. Here, that gives me my result, 43 times the sine of 29 degrees over the sine of 99 degrees. And that is an exact solution, but these problems call for an approximation. They're asking you to find a numerical value and round it to the nearest whole number. So here, it's going to sound strange, but an exact solution is actually too good. So here we're going to go ahead and find a numerical value that we can round. So here we go. 43 times the sine of 29 degrees is 20 point something or another. Now I'm going to go ahead and divide that by the sine of 99 degrees, and that'll give me approximately, now remember we're rounding everything to the nearest whole number, so 21.10 something something something, that's about 21 centimeters. About. So here, that'll give us about 21 centimeters. And there we go. From the 3 original pieces of information, we had originally 2 angles and a side length. We now find the entire triangle. And so that's the end of our problem. All right, so now let's have another example. Let's take a look now at, let's have one that doesn't draw the triangle for you. You'll note that the actual drawing is not necessary. It's nice to have, and if you'd like, you can draw your own. But all that's really required is that you know the information that's given. So here, the question is solve the triangle. And the information given is, we don't know the angle A, but we know the angle B is given by 42.57 degrees. The angle C is given by 71.83 degrees. And we know that the side length A is given by 2.6 centimeters. We don't know the side lengths B or C. So go ahead and give this a try. Pause the video for a moment, and once you've reached an answer, go ahead and unpause and we'll go through it together. All right, so let's take a look. First of all, we have 2 angles. We're missing a third. That's the first thing we should resolve here. We know for a fact that the sum of the 3 angles of any triangle is 180 degrees. And so if we're looking for the angle A, that must mean the B and the C are subtracted over here. So A must equal to 180 degrees minus B minus C, which is 180 degrees minus 42.57 minus 71.83, which, since you don't want to see me add and subtract decimals by hand, here, let's just go ahead and pull this out here. So if we take 180 minus 42.57 minus 71.83, we end up with 65.6, which of course we can also do by hand. Right? So here this will give us 65.6 degrees, and these are all in degrees. All right, so 65.6 degrees, that gives you the angle A. Here, this is written out to 2 decimal places, so we might actually just fill it in to make sure we keep the same level of precision. 65.60 degrees. We want everything to be to the same level of precision. So here, this is our missing angle. And now we can find our missing side lengths using the law of sines. Here we have that the sine of the angle A, and here we can go ahead and use this one because this is a precise value. We have exactly this amount, no rounding occurred. The sine of 65.60 degrees divided by the side length 2.6. That's going to be the sine of any of these angles divided by the corresponding side. So sine of 42.57 degrees over the side length B. All right? A with A with A, and B with B. And now we can solve this. Let me go ahead and multiply both sides by 2.6b by 2.6b. Here the b's divide away. Here the 2.6 divides away. And we're left with b times the sine of 65.60 degrees. That's going to be equal to 2.6 times the sine of 42.57 degrees, just like that. And now we can divide out by the sine of 65.60 degrees to isolate our b. Just like that. So that means b is equal to, the exact value is going to be 2.6, there's a point there, 2.6 times the sine of 42.57 degrees over the sine of 65.60 degrees, just like that. And that is the exact value, but again, in application, the exact value is actually too precise because here, these numbers are measurements down to a level of precision of 1 decimal here. Our lengths are 1 decimal. So here, this is too precise. It's not justified given the amount of information that was given. So here, we're going to round this off. Let's see here, 42.57. Oops, 42.57. There we go. I'm going to take the sine of that. I'm going to multiply by 2.6. And then I'm going to divide that by the sine of 65.60. And that'll give me a reasonably small number here. That'll give me 1.9313. Well, yeah, but we're rounding to the nearest 10th place. So here, this rounds off to 1.9. Approximately 1.9. Just like that. And that gives us our angle. That gives us our side length B, rather. And now we can use the same technique to find the side length C. Once again, this was a rounded value. Right? That's not exactly 1.9. It's only about 1.9. So we don't want to use rounded values if we can avoid it. Here, we're going to use the law of sines again to find C, but don't use these. Go back to the ones that had the higher precision, the ones that were measured originally. All right, so let's go ahead and use the law of sines one last time here. I can write this as the sine of 65.60 degrees over 2.6 is equal to the sine of 71.83 degrees over the side length C, which we don't know yet. Here, let me multiply both sides by 2.6c. Here the c's divide away, and here the 2.6 divide away. And this will leave us c times the sine of 65.60 degrees is equal to 2.6 times the sine of 71.83 degrees. Just like that. And now if we divide both sides by the sine of 65.60 degrees, divide on both sides by sine of 65.60 degrees. Here, these divide away, and I'm left with C is equal to 2.6 times the sine of 71.83 degrees over the sine of 65.60 degrees, just like that. And now, of course, that is the precise answer, but once again, that's actually too precise. So let's go ahead and give ourselves a nice numerical approximation here. If I take 2.6 times the sine of 71.83 degrees, that's going to give me that number. And then if I divide that by the sine of 65.60 degrees, that's going to give me 2.712634805. But of course, we're trying to get just a one degree, we're trying to get a level of precision of the 10th place, one space after the decimal. So here, we're going to round that off to 2.7. So even though that does go on quite a lot longer, we round that off to 2.7 approximately. And that is it. That gives us our last unknown. This will be 2.7 centimeters, and that's the end of our problem. One thing to note, this will come in handy later when some of these problems start having different kinds of methods that we need to use simultaneously. As a quick sanity check, notice the shortest angle is paired with the shortest side. The biggest angle is paired with the longest side, and the angle that's in between, well, the side length is also in between. That's a good way to double check things. At the end, if you haven't made any major mistakes, the shortest side should be paired with the shortest angle. The longest side will pair with the longest angle. Think about that geometrically, and that should make sense. One hopes, yes. And finally, let's turn our attention to one last problem. Let's look at an application problem. All right. Let's say you're trying to measure a distance across something that's not accessible, a canyon, a river, something along those lines. So let's just, here we go. Here's our inaccessible river of lava or whatever. Okay, and we're not going to be able to cross that. All right, now, we don't have to cross it. We are stuck on one side of this object, but we are free to move around and observe things on our side. So let's say we're on this side. Well, I'm going to go ahead and set up two observation points. Okay. Now, over here on the other side, there's a marker. There's a tree or something that I can see. All right. Now, what I want to do is I want to measure the distance from here across to here. So this is my desired value. Okay. I want to find this distance. All right, well, again, I'm not allowed to cross this. I can't. It's inaccessible for some reason. But I can do whatever I want over here. So once again, I want to find these distance across from here to here. What I can do is I can find another observation point nearby on the same side of my obstacle. And I can measure the distance from here to here. And that's a distance of 655 yards. Okay. Now, from here, I can't come across, but I can establish a line of sight, and I can measure that line of sight. If I consider this straight line from my point to my other point of observation, I can measure these angles. I can't do anything to the angle on the other side because I can't reach it, but I can talk about these two angles. This angle is 102.3 degrees, and this is the angle 32.5 degrees. And that's all the information that you need. You should now be able to find the distance across this obstacle. You should be able to find the distance from this point over to our marker on the opposite side. So this doesn't use anything different from what you've seen. Go ahead and pause the video, give it a try, and once you're done, go ahead and unpause the video, and we will go through it together. All right, so let's take a look here. This is nothing more than a triangle. Now, of course, it's not a right triangle because this is not gonna give you a 90-degree angle. Notice this is already over 100 degrees. So if this was 90, that would be over 190 degrees. That can't happen for a triangle. Before we get started, I'm going to go ahead and make some labels. I'm going to call this the angle A, I'm going to call this the angle B, and I'm going to call this the angle C. Just for convenience, when we do our computations, it's nice to have things labeled. So here I know the angle A, and I know the angle B. I don't know the angle C. Well, yeah, but that's easy enough to find out, because the angle C is what you get after you subtract these two angles that you already know from 180. So it's 180 minus 102.3 minus 32.5 degrees. And that's going to give you 45.2, I think. Yeah, 45.2. He can do all this other stuff, but he can't subtract. Yeah, that's right, 45.2. So now we have this angle C. Okay, so that's an angle we found. This doesn't require any rounding. Notice if these are exact, and so is that one. So that's 45.2 degrees. Well, now what I'm looking for is this side length here. Well, that's opposite of the angle B. Okay, so that must be side length little b. So what I'm looking for is the side length little b. Okay, well, from the law of sines, I know that the sine of capital B over little b is equal to, notice here I have the side length little c. I know that one. I measured it because it was on the same side of the obstacle that I was. So here, let me pair these two together. Sine of c over c. Because I know both capital and little c. Here, we're not going to need to find the side length a. That's not what we care about. We only cared about this distance. If you found this one also, that's fine. But again, the problem only is asking for this. So that'll be sufficient. All right, well, the sine of b, well, I know b, that's 102.3. So sine of 102 and 3/10 of a degree divided by the side length b, well, we don't know what that is yet, is equal to the sine of the angle c, which is sine of 45.2 degrees. That was so close to being a nice number, right? We know the sine of 45 degrees, 45.2, not so much. Divided by the side length c, which is 655, like that. And now we can simplify. Let me multiply out by the common denominator. I will multiply by 655b. I will multiply both sides by 655b. Here, 655 divides away, and here, b divides away. So this will give us 655 times the sine of 102.3 degrees is equal to, that's going to be b times the sine of 45.2 degrees. And now we can go ahead and take this and divide away that number we don't need. We're trying to get the b by itself. So we're going to take 45.2 degrees. We're going to divide that by, that should be sine of, right? There we go. And same thing over here. We're going to divide that by the sine of 45.2 degrees. These divide away, and that leaves us just our side length b, which is apparently equal to 655 times the sine of 102.3 degrees divided by the sine of 45.2 degrees. Just like that. And while that is a precise value, we're not looking for the exact value, right? Because here what we're looking for is the distance across, and here our level of precision is to the nearest yard for distance. So here we're going to go ahead and find an approximation. So let's go ahead and do that. Oh, let's see here. If we, there we go. So let's go ahead and take 655 times 102.3. We're going to take the sine of that, and then we're going to divide that by the sine of 45.2 degrees. And that's going to give us 901.90423335. But of course, we don't want all that. We just want this to a precision of the nearest yard. So here, if we round this to the nearest yard, that's 901.9. That'll round up to 902. So here, this rounds up to 902 approximately, and that is our result. So here, our distance across from the point A to the point C is going to be 902 yards. Just like that. Now, if you'll remember, we had the axioms of congruency for triangles, which stated that as long as we had the three pieces of information about a right triangle that were either all three sides, two sides and the angle in between them, or two angles and the side in between them, then we could uniquely determine any triangle. However, there are other combinations of information besides those three. So if you happen to have a different combination of information, then you would not necessarily have a unique triangle. So then that means that you don't have a unique triangle? Well, no, so here's the thing. You might. That's why this is called the ambiguous case. The ambiguous case is one where you might have a unique triangle, or you might have several. In particular, the example that we saw was in the previous section was what happens if you have two side lengths and an angle that is not in between them. Right? Two side lengths and the angle, but not the one in between, but one that's on the outside of those two. This is the ambiguous case. And it's the one where you might have a unique answer, or maybe you don't. So let's take a look at some examples of this and see how we can handle that. Let's start off with an example. We're given some bits of information. We're told to solve the triangle, meaning to find the missing bits of information. And here what we know is we have a side length A given by 32.5 feet. We're given a side length C that is given by 59.8 feet. And we're given an angle C, which is given by 52.3 degrees. Now here, we're not given this side length B, which is something we're going to need to find. We're also not given the angle A or the angle B. So we're going to need to find all of those. All right, well, we begin by looking at this and saying, oh, look, we have the law of sines nicely set up. Because remember, for any given triangle, we know that the sine of A over little a, is equal to the sine of the angle B over the side length little b, which is equal to the sine of the angle C divided by the side length little c. That's the law of sines. So here I know side length C and angle C. So I know this full expression. And in fact, I know side length A, which means I know this bottom part here. So if I use this one and this one, all I'm missing is the angle A. So I can write that as the sine of A over little a. Well, I know little a, that's 32.5 feet, is equal to the sine of C over C. Oh yeah, but I know C, that's 52.3 degrees, over the side length C, which is 59.8 feet. Just like that. Okay. So sine of A, which we don't know, over little a, okay, there we go, is equal to the sine of C, which we know right here, over little c, which we know right there. Okay, so now that we have that, we can solve for our missing piece. Here, if I multiply both sides by 32.5, that'll isolate the sine of C. So 32.5 on both sides. And that's gone. And here we have the sine of A is equal to 32.5 times the sine of 52.3 degrees over 59.8. Okay. Now at this point, you've noticed that this isn't really any different from what we've seen before. In the previous section, we used the law of sines, and it worked pretty much the same way. But here, once we reach this part, this is where the ambiguity can come in. Because remember, the sine of A is equal to whatever number that is. Remember, there's multiple angles A, which can have that. Remember, on your unit circle, there are several numbers, there are several angles whose sine is any particular number. The sine function is a periodic function, which means if I say the sine of A is equal to this, A might be one of several different numbers. That's where ambiguity comes in. Here, this is a precise solution. This is an exact solution. But the thing is, we're not even sure if that solution works. So here, let's go ahead and give this a try. We could estimate this, but here, if we're going to estimate it anyway, let's go ahead and just compute 32.5 times the sine of 52.3, and this is all in degrees, so make sure if you're using a calculator, it's in degrees. And we're going to divide that by 59.8 degrees, 59.8, not degrees, and that's going to give us 0.430012789. Okay, I'm not going to round just yet because notice that's not my answer. That gives me the sine of A. Okay, well, if the sine of A is equal to this, well, first of all, is that possible? Well, sure. Remember, the sine of A has to be between -1 and 1. So if this number right here had been bigger than 1 or less than -1, then this would be impossible, which means there would be no solution to this triangle. That's one of the possibilities of the ambiguous case. In the ambiguous case, you might not get a solution. So here, note this part right here, when you get to this stage where you get the sine of A is equal to something, this must be between -1 and 1. Otherwise, you will have no solution. Okay, but here, that is between -1 and 1. Okay, so let's see what we can get here. Here, I can take the inverse sine of both sides. Okay, so this does work out to be between -1 and 1. So now I can take the inverse sine of both sides. So here, A is equal to the sine inverse of 32.5 times the sine of 52.3 degrees over 59.8. Okay, well, I already know what that number is right here. That was that 0.43 number that I had. So now I just need to take the sine inverse of that. So let me take the sine inverse, and that'll give me 25.468. Right? Now, of course, here all of our degrees are rounded to the nearest to our nearest tenth place, the first decimal digit after the decimal. So here I can round this off to 25.5. Okay, very nice. This will be approximately 25.5. And you say, okay, well, that wasn't very ambiguous. I mean, yeah, okay, maybe there was no solution. But as long as there was a solution, there we go. I found what my value A must be. So let me go ahead and put it right here. Well, that is a correct value. Here, this is 25.5. But we might be missing another one. You say, what do you mean missing another one? Well, here what we're saying is the sine of A is equal to that number. Well, think about what the graph of the sine function looks like. The graph of the sine function looks like this, where the sine function is periodic. So it's going to go up and down and up and down like this. Okay, so here I just found that this is 25.5 degrees. Okay, cool. You say, how do you know that's right there? Oh, because on the sine function, you start from 0, you go up to 360 degrees. And so here in the middle, this would be, what, 180 degrees, yeah? So here, this right here would be 90 degrees. And so 25.5 must be here before 90 degrees. You say, yeah, so? Well, look. If I take sine of 25.5 degrees, I'm going to get some number. That was that number that I just got right here. Well, yeah, but notice there's other numbers that do that. There's another one right there on the other side of 90 degrees. You say, well, there's more of them, aren't there? I mean, over here, I have another one. And over here, I have another one. There's an infinite number of them, right? There's one over here, and there's one over here, and one over here. Yeah, but those couldn't possibly work. Because remember, what we're looking for are the angles of a triangle. The biggest angle of a triangle couldn't get to 180 degrees. Because remember, if you add up all three angles of a triangle, that has to add up to 180. So here, I can't have any one angle be more than 180. So here, nothing over here could possibly work. Also, I can't have a negative angle. Right? It's a triangle. My angles have to be at least 0. So here, it couldn't be any of these because those are all negative. But that still leaves these two possible answers. You say, well, what I know this one, that's that 25.5, but what is this one? Well, here we can take advantage of some symmetry. Because notice, I'm going to take this and I'm going to blow it up a little bit. Let's make it a little bit bigger. Here, I'm just blowing up this part. If this is 90 degrees, this is 0, this is 180. The angle that I found from my calculator was 25.5 degrees. Okay? And that's all the calculator will ever give you. It's up to us to know that there's another possible one. Here we're going to take advantage of symmetry. Remember, sine and cosine graphs are symmetric. They have lots of regularity. And here, if this is 25.5 degrees toward the right from the beginning, then over here, this must be 25.5 degrees to the left from the end. So if this is 0, go forward 25.5. If this is 180, go backwards 25.5. So here, this angle would be 180 minus 25.5, which would be 154.5. So up here, this A could be 25.5, or maybe it is 154.5. You say, so which one? Well, maybe both. You say, well, how do you know? Well, look right here. If you add these together, right here, 25.5 and 52.3, that's going to give you 77.8, which leaves you lots of extra room to find a third angle, because those don't add up to 180 yet. But if you add these two together, here you know for a fact that's the right angle, because that was given to you. If you add these together, that's 206.8. That's already too big. So that's how you check the ambiguous case. In the ambiguous case, you're going to have three possibilities. The ambiguous case will either have no solution, it'll have one solution, or it'll have two solutions. You see from my graph over here, it couldn't possibly have more than two. It's possible not to have any, and this is where you'll find out if there are none. If there are none, well, then you're done. If there is some, then you're going to find them both. And then to tell, okay, is it just one of them or is it both? You're going to test right here. You're going to check, okay, if I add these together, is there any more room for another angle? If there is, great, that one works. Here, if you add these together, is there any more room for another angle? Nope, no, there's no more room. Okay, so that one isn't possibly a correct answer. So what that means is that here there's only going to be one solution. This one does not work. So we only have one solution. All right, so now we can go ahead and finish this off. Here we're missing an angle, and that one's going to be just the difference. If we take 180 minus the two angles we already have, minus 25.5 and minus 52.3, if we subtract those, we end up with 102.2 degrees. Okay, so that is our angle B. This is 102.2 degrees. All right, so we found this one. We found this one. And finally, we can go ahead and find our last remaining side. Now, here, this was something that we found using the inverse sine function, and we rounded it off, right? That was not exactly right. So here we're going to avoid using that one. Here, let's use these two, because these were known. These were measured and given. So let's go ahead and use the law of sines to finish our last part here. And the law of sines tells us that the sine of the angle C, which would be 52.3 degrees, divided by the side length C, which is 59.8, is equal to the sine of the angle 102.2 here. What wait, where did I go? Oh yeah, here we go. The sine of, right, 102.2 degrees over b. Now at this point you might protest and you might say, well, wait a minute, you told us not to use that one because that was one that we found and that was going to be rounded and that's imprecise. Well, then why are you using this one? This is also one that we found, right? Wouldn't that be imprecise? The answer is yes, it would, but we don't have much of a choice because notice the only way for us to get this using the law of sines is to use, the only way for us to get this using the law of sines is to use this one. So here my options are either not get an answer, which is not a good option, or use one number that's imprecise and one that is, or use two numbers that are imprecise. Oh, well, using two is definitely the worst option. So here, yeah, I'm going to have to use this one, even though it's imprecise. But if I don't use that one, I won't get that answer. Here, I do have the option between these two, so I'll use the one that is precise. All right, so here, that's going to be b divided into the sine of 102.2 is equal to 59.8 divided into the sine of 52.3. And that's the last computation. Here we can go ahead and multiply both sides by the common denominator. We can multiply 59.8b, 59.8b. These numbers divide out, b divides away, and we're left with b times the sine of 52.3 degrees is equal to 59.8 times the sine of 102.2 degrees, just like that. And now to find our b, we can go ahead and divide both sides by that number, and that makes us happy. Just like that. Here these divide out, and we get our answer. b is equal to 59.8 times the sine of 102.2 degrees divided by the sine of 52.3 degrees. And of course, we're looking for an estimate, right? Here we're looking for numbers rounded to the nearest tenth of a foot. So that all goes into a calculator so that we can find an approximation. Here we don't want a precise answer. In applications, we typically want an imprecise answer up to our level of precision. Basically, this answer is too good. So we're going to take 59.8, multiply it by the sine of 102.2, and then we're going to divide that by the sine of 52.3, and that'll give us that side length there, 73.87225.992. Well, yeah, but once again, everything's being rounded to the nearest tenth. So here we can round this to 73.9, and so that is our result, 73.9. Approximately 73.9. And so here that's 73.9 feet. And there we go. Given our three original pieces of information, our little a, our little c, and our capital C, we were able to find all of our possible answers. Notice here is a quick check. You also note that the smallest angle is opposite the smallest side. The largest angle is opposite the largest side. If ever that doesn't happen, there's clearly something wrong, so we can go back and figure out. All right, let's take a look now at another example. We're still looking at the ambiguous case where we may have either no solution, we may have just one solution, or we may have two solutions. Those are the only three possibilities, either none, one, or two. So let's see here. Example, let's go ahead and solve the triangle. That's given with the following information. We're going to say the side length little a is 72.08 feet. We're going to say the side length little c is given by 79.86 feet. And the side length c is some unknown amount. We need to figure that out. Likewise, the angle A is going to be given by 51.20 degrees. The angles B and C are currently unknown to us. All right, so here we go. We're going to begin by setting up the law of sines, and here, well, there's only one possibility. Sine of A over A and sine of C over C. We know nothing about B. So here we go. Sine of A over A is equal to sine of C, which we don't know, over C. Now we can solve for C. Here we can multiply this to both sides. Multiply both sides by 79.86. Those two are gone. And this leads us to the sine of C is now by itself. Sine of C is equal to 79.86 times the sine of 51.20 degrees over 72.08. And we can compute that, and that'll get us, oh, let's see here. I'll take 51.20, take the sine of that, multiply that by 79.86, gives us 62 point something or another, and then I'll divide that by 72.08. And that gives me 0.8634 something or another. All right? Remember, if this number is not between -1 and 1, we're done, because this won't have a solution. You can't have the sine of an angle not be between -1 and 1. But because this is between -1 and 1, it's 0.8, give or take, then this can continue. Okay, so what we want to do is we want to take the inverse sine of both sides. That way the C is isolated. And now we're taking the inverse sine of all of this stuff. 79.86 times the sine of 51.20 over 72.08. Now, we already computed that part. That was that 0.86 that we did just a moment ago. So now all we need to do is take the inverse sine of that. The reason we compute that first before the inverse sine is to make sure that it actually can be done. So now we take the inverse sine, and that's 59.70689925. But of course, notice we're rounding all of our degrees to the second digit, to the hundredths place. So we can round this off to 59.71. This rounds up to the next digit. So 59.71. Okay, so here C is approximately 59.71. Or, now remember, whenever you take the inverse sine of a number, there's going to be two possibilities. It's either going to be the number that calculator gives you, and or this number, the one on the opposite side of your graph of this part of the period of the sine graph. It's pretty predictable though. Whatever number this is, if you subtract it from 180, that'll give you your other number. So here, if our calculator gives us 59.71, the other possibility is 180 minus 59.71, which is 120.29. Just like that. All right, so now we say, okay, but now we got to check these. I say, well, how do you check? How do you know if one works or if both work? Well, here, consider these two added together. That's 110.91. Oh, that's less than 180. So that's fine, because that'll give me room for a third angle. Okay, but now let's add these. If we add these together, that'll give us 171.49. Well, that's also less than 180, which gives us less room for an angle, but it still gives us room. So here, if you add these together, that's less than 180. If you add these together, that's less than 180. So that means in this case, we will have two solutions. Here, note, at this point, if this part is not between -1 and 1, there is no solution. Okay. Right here, this part and this part as well, when you add together the angle that was given to the angle you just found, if you add together 51.20 plus 59.71, because that's less than 180, that means there's room for a third angle. So here, this is a valid solution. Over here, if you add together 51.20 degrees plus the 120.29 degrees, that is also less than 180. Less than 180. So that is also valid. So that's how you can tell. At this point, you can tell whether there is a solution or not. At this point, once you get these two answers, you'll be able to tell, oh, either maybe just one of them works, the one that's less than 180, or both of them work, because both of them give you a sum that's less than 180. So in this case, we're going to get two solutions. The way this book does it is it writes two solutions like this. They say, okay, that'll be our first solution there. Our second solution, they call it A prime, B prime, C prime. They put a little tick mark above it just to be able to distinguish it between the first answer and the second answer. So here, the A and the A prime are the same. Those are the given information, 72.08, the capital A, 51.20 degrees, and the little c, 79.86 feet, like that. Those numbers are the same. What's going to now start being different are these numbers that we're going to find. All right, so let's see. We just found C, and C could either be 59.71 or it could be 120.29. So for one of the C's, I'm going to go ahead and say, okay, that's 59.71, and that's an answer that I found. Or in the alternate version, I could have the angle C being much larger, 120.29. Just like that. And now I have two separate triangles. At this point, they stop interacting. Now I have two separate problems. I need to find B and capital B. I need to find B prime and capital B prime. And those will be handled completely separate from one another. So you can now think of these as having just two completely separate problems. So go ahead and continue. Go ahead and give this a try. See if you can finish out the triangles. Find the B, the capital B. Find the B prime and the capital B prime. Once you have gotten an answer, or rather, two answers, go ahead and unpause the video and we'll go through it together. All right, so let's go ahead and start with this triangle here. I know capital A and little a. Here, I can find this missing angle. Now, because it's relying on an angle that we found that was estimated, it's not going to be precise. But, oh well, we won't have an option but to use it to find little b here. So, I want to find capital B, and that's going to be 180 minus the little a, minus the capital A, minus the capital B. And if I subtract all of those, so that gives us 69.09 degrees. So that's our angle B here, 69.09 degrees. Note that that's got no relation to this one here. These are separate triangles now, so we'll solve each of them on their own. Here, we could do this one. In fact, let's just focus on this one now, and then we'll do this one on its own. All right, so now we've got everything we need to set up the law of sines here. We don't want to be using more imprecise information than we have to. Here, we have to use this one because it's the only way to set up the law of sines. Here, we have the choice of either using this pair or this pair. This pair is something we found, which means it has some errors, some rounding errors. So we're going to use these instead. So the sine of the angle A, 51.20 degrees, divided by 72.08 is equal to the sine of 69.09 degrees over, some unknown amount. So now we can go ahead and solve for B. If we multiply on both sides by our common denominator, we're going to go ahead and multiply by 72.08b. And same thing over here, 72.08b. These numbers divide away, and we're left with b times the sine of 51.20 degrees equals 72.08 times the sine of 69.09 degrees. And finally, we can go ahead and divide out by the sine of 51.20 degrees. The sine of 51.20 degrees. And this gets us our b is equal to 72.08 times the sine of 69.09 degrees divided by the sine of 51.20 degrees. Just like that. And now that is our exact answer, but we can go ahead and approximate that because here we need estimate up to 2 decimal places. So here, that's going to be 72.08 times the sine of 69.09 degrees divided by the sine of 51.20 degrees. And that'll give us 86.39765,112. But again, we're rounding to the nearest hundredths place right here. So our side length B would round off to the nearest hundredths place, which for this instance would be 86.40. So that'll give us our final side, 86.40. As a quick way of checking this to make sure we haven't made any egregious errors, the biggest angle should be opposite of the biggest side, and the smallest, I have that backwards, don't I? The biggest side should be opposite of the biggest angle, and the smallest side should be opposite of the smallest angle, which in fact it is. So we haven't made any egregious errors at least. We still have another triangle to solve. We're going to do this the same way. The computation is very similar, but now we're looking for B prime and capital B prime. So let's go ahead and go through that. Let's see here. We have 2 angles, and we're missing a third. Okay, so if we take 180 and subtract away the 2 angles that we are already have, we can find the missing angle. So let's go ahead and do that. If we take 180, well, let's find this up here. All right. If we take 180 and we subtract away the 2 angles that we already have, that'll give us the angle B prime. 180 minus 51.20 minus 120.29. And if we subtract all of those, we get 8.51. And again, that's an angle. So here our B prime would be 8.51 degrees. Okay, so that's what we find. And finally, we can set up the law of sines again. Here, the sine of A over A will be equal to the sine of B over B. So let's give that a try here. Sine of A, which is 51.20, over the side length A, 72.08, is equal to the sine of B prime, which is going to be sine of 8.51, over the side length B prime. That's what we're missing. We can now solve for B prime by multiplying out by the common denominator here. If I multiply by 72.08 times B prime on both sides, 72.08 times B prime, just like that. Now I can go ahead and divide these numbers and divide B prime into B prime, and we're left with B prime times the sine of 51.20 degrees is equal to 72.08 times the sine of 8.51 degrees. And finally, we can divide both sides by 51, the sine of 51.20 degrees, just like this, just like this. And now we isolate our b prime, which is given to us as, well, we can compute this. All right, let's take a look here. That'll be, we want the sine of 8.51 degrees. We want to multiply that by 72.08. That's our numerator. And now we're going to divide that by the sine of 51.20 degrees. And that'll give us 13.68667359. But of course, we're trying to round everything to 2 decimal places. So this is approximately 13.69 if we round off to 2 decimal places. So over here, that means that our b prime is approximately equal to 13.69. So over here, that's going to be our b prime, 13.69. And looking now at our second triangle, we can double check to make sure that this is at least reasonable. The smallest angle is opposite of the smallest side. The largest angle is opposite of the largest side. So we at least haven't made any egregious errors. This does at least match up with something that is a reasonable result. Right? And that is our result there. All right, so now let's take a look at one more example. Let's see here. So let's go ahead and solve the triangle, which is given by the angle B is equal to 72.4 degrees. The angles A and C are unknown, so we don't know what those are. We know the side length B is going to be 650 centimeters. And we know the side length C is going to be 1,225 centimeters. So here we can solve for little a, capital A, and capital C. So go ahead and give this a try. Pause the video and see what you get. All right, so let's take a look. Here we can set up the law of sines by taking these two. The sine of B, which is 72.4 degrees, over the side length B, 650, is equal to the sine of the angle C, which we don't know yet, sine of the angle C, over the side length C, which is 1225. Now, we can go ahead and solve for C. Let's go ahead and get rid of that 1225 from there. Let's go ahead and multiply it over to both sides. These two divide away, and we're left with the sine of C is now by itself, and that's equal to 1225 times the sine of 72.4 degrees over 650. All right. So now we go ahead and check to see what this is. That's going to be 72.4. Take the sine of that. We're going to multiply that by 1225. And then we're going to divide that by 650. And that's going to give us, oh, that's a problem, right? Because remember, what we just found was that the sine of that angle C is equal to this number. But this number is about 1.8, 1.796. That's not possible. Here, the sine of any angle must be between -1 and 1. Here, this is approximately 1.70, approximately 1.8. Here, this is not between -1 and 1. And so what that means is that this is not possible. But if this is not possible, then that means that this angle can't be found. So it's not that we find multiple solutions, it's that we can't find any. So that means that here C is undefined. And so that means that there is no such triangle. And there we go. That's our result. Okay. So that is it for this problem. In fact, that is it for this section.